So first concept we have to discuss here, AC applied to a resistor. We already know about resistor. Resistor means it is a device which will oppose the flow of current through any kind of a circuit. To explain this, what is our heading is AC should be applied to resistor. Let's take a circuit which consists of resistor and an AC source. I am taking connected an AC source, and this is a resistor of resistance R, and through this there is a flow of current I, and potential or voltage which is given by this is V. V is the potential that is given by this AC source. It is a voltage given by this source, which is equal to, it is a standard form of equation. V is equal to Vm sin omega t. Okay, omega t means nothing but theta. Theta is equal to omega into t. Omega means angular velocity. Theta by t, it is equal to omega. So using that equation we have written this sin omega t, which means sin theta. So V is equal to Vm sin omega t. This is the voltage which is given by this AC source. So whatever the voltage present in this will give some will produce some current, because since the circuit is a closed one, there will be a potential difference. Because of the potential difference, current will flow. Current will flow like this. Once the current is started to flow, it will also flow through the resistor, and it will develop some other potential there. It will create some potential around this resistor, because there is a resistance offered by that resistor. So that is why there will be potential is developed. So that is why whatever the potential developed here, that should be equal to this. Okay, whatever the potential here is, that should be equal to the resistor. Because if you wanted to calculate the potential around this, or if you wanted the potential around this, you have to hold in two common points only. Hold the voltmeter in two common points like this. For example, if you wanted to find out potential around this, you have to hold the voltmeter here. If you wanted to find out the potential around the resistor, again you can hold like this. That is why whatever the voltage present around this should be equal to this. Okay, this is the concept. Now, and one more thing is, this value V is equal to Vm sin omega t, which is a potential by the AC source, and that potential is called as an instantaneous values of potential. Instantaneous means at a very small interval of time. Yes. The instantaneous value of the instantaneous values of potential around AC sources, V is equal to Vm sin omega t. Then what is the meaning of Vm? Vm is called as a peak value of voltage, or I said that peak means is maximum one. It is the maximum value of voltage. Okay, or you can also say that it is a voltage amplitude. I'm using different terms, but they're one and the same. They're all having the same meaning. I've used three terms for a one quantity. Vm is called as a maximum voltage and can be called as a peak voltage. It can also be called as a voltage amplitude. They are all one and the same. Okay? So V is equal to Vm sin omega t. Now apply KVL. Applying KVL to the loop. You have to apply the KVL to this. So once you apply the KVL, sum of the potential around the enclosed surface is equal to closed circuit is equal to 0. Yeah. So that what we can write is potential around this and that, which is equal to V is equal to, I can write I into R. Okay? Yeah. Sorry, 1 minute. Yes, this is correct. V is equal to I into R. Then whether this is correct, because we have applied the KVL, right? Now what we have to do is take the IR to this side. What will happen is it becomes V minus IR, which will be equal to 0. So V minus IR will be 0, which tells that summation of M is equal to 0. So which is one and the same. Directly written, I have taken IR to the RHS and written. Okay? So V is equal to I into R. V is the voltage across this resistor, and voltage across this resistor is also equal to voltage across this source. What is the voltage across this source? That is V is equal to Vm sin omega t. Let's write here. V is equal to Vm sin omega t is equal to I into R. Let's rearrange. Already we found the value of V. That is V is equal to Vm sin omega t. This is the value of voltage. And let's write the value of I here. We wanted to find the value of I. Take the R to the other side, which becomes Vm by R sin omega t. Now, we have written I is equal to Vm by R sin omega t, and we can write this as Vm by R can be replaced with another term. It can be written as Im sin omega t. See, this is the equation we have got for the current, which is flowing through that circuit. I is equal to Im sin omega t, where Im is equal to, we have written Vm by, okay, where Im is equal to Vm by R, and here Im is called as peak value of current or maximum value of current or current amplitude. Okay, this is the value for equation for current amplitude, maximum value of current or peak value of current. They are all one and the same. So I is equal to Im sin omega t. This is the equation we have got. And for the voltage in the pure resistive circuit, this circuit can also be called as a pure resistive circuit because there is only a component called resistor. That circuit consists of only a resistor, that's why it is known as a pure resistive circuit. So in the pure resistive circuit, we got the equations for voltage and current. If we look at these equations, in the place of V, here we have I, in the place of Vm, here in the place of Im, in the place of sin omega t, here we have sin omega t. Mainly here we have to focus on the angles, that is omega t and sin omega t and sin omega t. They are one and the same. That is why here what we can say is there will be no phase difference between current and voltage. Then what is this? What is a phase difference? We have to understand. Now phase difference, I already told you, if you want to represent the AC, we will use a sine waves. It is a way of graphical representation of AC, and where you can see some positive parts curve in the positive section, and you can also see some part of a curve in the negative section. So upper face and lower face. Again I am drawing here. See, this is a positive one, this is negative. Okay, so this can be called as a phases. This is a positive phase, this is a negative phase. And while representing the current, if you wanted to represent current and voltage, it is possible, because while explaining the graphical representation, I told you that along the y-axis we can take we can take the voltage or current. Okay, that is why to see the relation between current and voltage, here we got the equations for voltage and current. So to see the relation between current and voltage, we should draw the graphs. Okay, and let's write phase relation using a diagram called Phasor diagram. Okay, Phasor diagram is which gives a relation between phases of current and voltage. So such a diagram is called as a Phasor diagram. In other words, what we can say is it is a vector which rotates about a origin with the angular speed omega. I will explain the meaning of that phasor. Phasor means it is a vector which can be rotated about a origin. It can be rotated about an origin with the angular speed omega. I will explain what that definition says. So I told you that we should draw the phasor diagram to show the relation between current and voltage. Phasor diagram. These are important. Phasor diagram. Okay, let's draw. So let's we can take VRI here along y-axis. We can take omega t along the x-axis. Now let's write. This is the voltage phasor. Okay, this is a phasor for voltage, because we have two equations here. Okay, so phasor for voltage. This is the phasor for current. See, this is the phasor for current. We have drawn two graphs for current and voltage. Now let's see here. See, these are the peak values of current and voltage. Okay, that is written as here it is Im, peak value of current. This is a Pm, peak values of voltage. Vm, Pm and Vm. Okay, and this is an angle. What is that angle? It is pi by 2. At the angle pi by 2, current and voltage reaches a maximum value. See, at this time you can take the angle or you can take the time. At this time or at the angle pi by 2, these two graphs reach its maximum value, correct? Im and Vm. And when it is pi, at this time both the graphs reach to 0 value, which is a minimum value. Okay, see here. If you go up in this axis, the value will increase. If you come back to that place, that position, there is a decreasing value. So 0 value here. Once you go up, there is a plus values, and there is a negative values when you move downwards. So they will reach minimum value. Again they will increase, but they are in the negative axis. Again they will reach the maximum value here at the same angle. Again they will come to 0 at the same angle. So that is why what we can say here is the current and voltage are in phase each other. They are in phase. Phase means they have to reach the maximum value at the same time. They have to reach the minimum value at the same time. See here, that is happening here. Both the curves will have the maximum value at the same time. They are having the minimum value at the same time. That is why the current and voltage are in phase in the pure resistive circuit. Or in other words, what we can say is there is no phase difference between the current and voltage. Why? Because they are reaching the maximum minimum values at the same time. There is no lagging, there is no leading, which means what I am telling you that there is no gap between the current and voltage when they are reaching to some values. Okay, that you are not going to see there. That is why there is no phase difference between current and voltage. They are having the same phase at the same time, and they will reach the maximum value and minimum values at the same time. So this is an understanding from Phasor diagram. So further, let's draw here Phasor 1. So let's take 2 points here. See, these are the 2 points, and see here they are reaching the maximum value. Let me take these 2 points. Okay, at the same time I am taking. So there should be the angle same. So at the same angle I am drawing the 2 lines. See here. What is the angle? That is, let me say, omega t. Okay, what is the angle here? That is omega t. At the omega t angle, this is a current phasor, right? This is a current phasor, this is a voltage phasor. Okay, they are at the same angle. See, same angle you can see. I have taken 2 points and I am trying to write its phasor diagram. Now, what is the value of this phasor? That is, we are trying here. V means it is Vm sin theta. Okay, and the value of current I equal to Im sin theta. Okay, so this is known as a phasor. Okay, it is known as a phasor, and phasor means a vector because it is rotated. That is why it is called as a vector, which doesn't mean that voltage and current are vector. Okay, so this is a concept we are following from the olden days. That's why we are saying it as a vector itself even today. So this is a vector which can be rotated about this origin. See, we can rotate like this with the angular speed omega. So that is the definition of phasor. Phasor means it is a vector which can be rotated about the origin with the angular speed omega. So this part from 0 to 90 degree we should fall in first quadrant, right? That is why we have drawn this phasor in the first quadrant. For example, you have taken the points here, I should draw in the second quadrant. Okay, this is a phasor diagram. Now here we have written Im, which is equal to Vm by R. Im means it is a peak value of current. Now let us find the power loss in this circuit. Power loss means energy loss in this circuit. Whenever the current flowing through that will heat it up, so there will be power loss. So let's write power loss. So power, I can say power loss or power dissipation. One and the same. It is called as a instantaneous. Instantaneous power dissipation in pure resistive circuit. Let's find P. P is equal to power dissipation. Formula for power dissipation is I square. That is a formula to find the power. I square R. I is equal to, we already know the formula. I is equal to Im square into R sin square omega t. Im sin omega t, which is the formula for I. We have to square it. Im square R into sin square omega t. So this is the equation for instantaneous power. Then what is the average power over one complete cycle? Then which is called as a one cycle. See here. This one is called as a one cycle. Okay, this is a one cycle. Or in other words, we can define like this. See here. If I draw like that, the distance from this crest to crest is known as a wavelength. These are some terms you should know. The distance from here to here is called as a wavelength. Crest to crest or trough to trough. Okay. So that is known as a wavelength here. Yeah. So the power. Now power dissipated over one complete cycle we have found. Whatever we calculated here, it is an instantaneous power dissipated. For a very short interval of time, what is the power dissipated? That is P is equal to I square R, Im square R, sin square omega t. So over this cycle, what is the power loss? Let's find it. Average power loss is, how to find average power loss? Average power loss can be written like this. See here, P bar, it is equal to this way of averaging. Okay, averaging, which is equal to, what is P? P means Im square R sin square omega t. So here Im square R sin square omega t. See, why we are averaging sin square omega t? Because omega t is a variable. 3 times variable. That is why. So Im square R into sin square omega t. Now to find this, we have to take the integration. So once you do the integration, sin square omega t can be written as, there is a formula for sin square omega t, which is 1 by 2 into 1 minus cos 2 omega t, cos 1 minus, yes, cos 2 omega t. Okay, this is the formula for this one. Sin square omega t is also equal to 1 by 2 into 1 minus cos omega t. So now what we have to do? We have to integrate this. You cannot integrate this one. That is why you can directly write half minus cos 2 omega t divided by 2 you can write. If you integrated this part, because we cannot integrate this, that is why we left with the half here minus cos 2 omega t. If you integrated this, it becomes sin 2 omega t divided by omega. Okay, divided by 2 omega. 2 is already there. 2 omega is there. So it becomes 4 omega. Sorry. What you can write is 2 omega itself. So sin 2 omega divided by 2. Now 2 omega t, it means it is an angle. Over a complete cycle, if you take the complete cycle, what is the angle here? It is pi, 2 pi. 2 pi means 360 degree. Sin 360 degree means it is equal to 0. This whole term goes out, 0. So that is why what we have to do here is half. So that is why what you can write, P is equal to half into Im square R. So this is the equation for average power over one complete cycle. That is why the power is not 0. See here we have got the average power. P bar is equal to half into Im square R. That is why there is a power loss. Power loss is not equal to 0. So can we understand this with this concept, with the graphical? Yes, we can. So let's try to understand the meaning of power. Why power is not zero here? That is, we should understand here. Now let us take two graphs, this I and B, and also let's take the equation, this one. Or you can take, let's take the equation, this one, V and I. Power equal to voltage to current. You can also use that equation or you can use this equation. I hope that you already know it. See here, current is increasing. Current is increasing. That is why current should have positive value. Voltage is also increasing. It should also have positive value. So here P will be positive. Power is positive, right? Positive values. Again, this is decreasing. Still, it is positive. It is coming to zero. Still, current and voltages are positive. So here also you will get power is a positive. For this part of the graph, the power will be positive. Again, now the current is negative here because in the negative axis. Similarly, voltage is also negative. Current and voltage are negative. Minus into minus, plus. Again, here also power is positive. Again, here also it is decreasing one, but still current and voltages are negative. If you multiply it, minus into minus, plus. So again, here also power is positive. So if you take power over a complete cycle, see, everywhere power is positive. Everywhere power is increasing. That is why there is a power loss. So this is the understanding of power loss with the help of that graph. Now let's look at this equation. P bar is equal to half into Im square into R. But when we come to the DC, we represent the power as this. P is equal to V into I. Then we should think, is it possible to represent the AC power in the form as a DC power? I am repeating once again. Is this possible to represent the AC power in the form of DC power? Yes, it is possible by taking one new term which is called as a RMS. Okay, RMS current. RMS current means it is called as a root mean square current. Okay, RMS means it is a mathematical form. Okay, it is a mathematical form. That is why it is called as a root mean square. Square root of something, that is called as a root mean square. Okay, so why we are taking is root mean square. The concept of root mean square is used to represent the AC in the same form as DC. Okay, that is why we are using RMS. I hope you understood this. P is equal to half into Im square into R. Now what is our intention? We have to represent this power in terms of in the same form as a DC. Yeah, let's do it. So to define it, we should take one concept. What is it? It is called as root mean square. RMS current. Okay. How to write the RMS current? Let's write IRMS. It is equal to Im by square root of 2. Okay. This is the equation for RMS current. RMS current means it is a current equivalent to DC current which will produce a same average or same power loss as the alternating current would does. Okay, I mean whenever when the IRMS means it is equivalent to DC current, that current will produce the same power loss as the alternating current would does in any kind of a circuit. Which means that if you pass the AC current in a circuit, in a resistive circuit, it will generate, some quantity of power will be dissipated, and same amount of power is dissipated when this current is passed through that circuit. So that is what we can, what it is possible is, we can, it is possible to define the AC in the form of DC. Okay, so that is by taking the quantity IRMS. So value of IRMS is equal to Im by square root of 2. it is also equal to Im into 1 by square root of 2 means 0.707. Okay, this is a concept we have introduced. So now if you wanted to represent this power in terms of this, then power, we can write the power as, what is our equation? This one, P is equal to P bar. P bar means what is that? This one, half into Im square into R. See here, Im by square root of 2 is there. Square it on both sides, square on both sides, taking the square on both sides. IRMS square, Im square divided by square root of whole square means it is equal to 2 itself. That is why you will get Im square by 2, which is equal to IRM square. What we have here? 1 by 2 into Im square. That is what we can write is IRMS into R. See, this is the equation for power with the help of RMS current. Okay. So this is the concept of RMS current. RMS current means it is a equivalent to DC current. Which is equivalent to DC current, and which would give the same average power loss as alternating current would does in any kind of a circuit. So this is about power. In the similar way, we can also write RMS voltage. You can also write RMS voltage. How to write RMS voltage? So while proving the equation for pure resistive circuit, we wrote this equation. What is it? Im is equal to Vm by R. This equation we have what? Let me write like this. Vm equal to Im into R. Let us multiply 1 by square root of 2 on both sides. Multiply 1 by square root of 2 on both sides. So Vm by square root of 2, it is equal to Im by square root of 2 into R. So Vm by square root of 2, it can be written as Vrms. Okay. Vrms. Before that, I should write like this. Sorry, I should write like this. Vrms, it is equal to Vm by square root of 2. This is the number. Vrms is equal to Vm by square root of 2 or 0.707 into Vm. See, this is a representation of Vrms, similar to the IRMS. So this is about the concepts of VRMS, IRMS and AC.